Great. Well, thanks for having me. So I'm Ryan McDonald. I work at Google. This is a talk about a subset of the work that we're doing in scientific literature mining at Google. This is also work that I've done with some collaborators at the Athens University of Economics and Business, and I'm going to be talking about results on data sets that various efforts have put together, like BioAsk, Cord19, Trek, and that. Right. So before I start with the technical material, I'm going to kind of do a couple shameless plugs here. But actually, everything I talk about today is in the back end of these systems, so it is related. So the first is the COVID-19 Research Explorer by Google. And this is a tool that gets updated, I think, bi-weekly, twice a week, on the Cord19 data set. And this is Retrieval, QA, some QA behind it, as well as the ability to sort of refine and drill down on subsets of search results. The second is with my collaborators in Athens. This is the AWB COVID-19 search engine. And behind this is some of the technology that's been in the BioAsk challenge the past few years, and they've been the top group, reporting group in that challenge. Okay, so diving in, what do scientists actually need? And of course, that NLP can help with. There's a lot of different things, right? So I always kind of think about the paradigm where there's some scientists, they're doing a bunch of wet lab experiments. They have some results, they put those into artifacts, maybe like an Excel spreadsheet, and then they go to one of their favorite literature search tools to sort of find support for results, try to understand why that's the case, and then maybe even generate new hypotheses or new things to be tested, or write systematic reviews or something like that based on it. And that artifact then goes back and sort of informs the next round of experiments that have to be run. So of course, like the ability to sort of do a bunch of things with the literature, like aggregate evidence, refine on evidence, create artifacts like systematic reviews, verify hypothesis, link the literature and the results they have to databases, ontologies to do sort of search in that sense. All of these are important, but actually almost always, when they go to the computer, they start with some kind of search and evidence extraction, right? So looking for literature or looking for something and extracting the bits of evidence from that. So it is a bottleneck, and it is kind of the starting point to most search in this space. And so that's where this talk is going to focus on models specific to that particular problem. And people do a lot with tools like Google Scholar or Semantic Scholar, PubMed. When they search literature, there's kind of a head of the distribution, maybe searching for an author or a general concept like breast cancer or something like that. We're kind of interested more in these very heavy information seeking queries, right, where the user is looking for something very specific, or something where the answer may be across multiple documents, or maybe multiple valid answers to that query, this sort of thing. And actually, search engines have come a long way in the past 5 years, and they are getting better and better at handling these kinds of queries, but it's not hard to find cases where they don't do a great job. And sort of talking about the other things we might want to do with biomedical literature, as I mentioned, the jumping off point is often search. So we had a study on question answering in biomedical literature. This was part of BioAsk last year. And one of the things we showed is that if we take the best reporting retrieval model from that challenge, and we use that as input to a question answering model, versus taking gold relevant documents from the challenge and use that for the question answering model, you see a massive drop in performance. And that's to be expected, right? If you show the question answering model highly precise documents, it's much more likely to get the right answer. But it does show that, at least for those downstream problems, the headroom may not necessarily be in building better linkers or better QA models, but actually better retrievers, the first stages that sort of collate the information. So before I jump into some of the things we did, just kind of a little overview. Most people are probably, understand these pretty well, but to sort of make sure we're all in the same space. Typical IR systems take this form. And I'm not talking about, the Google.coms or sort of other ecosystems where people are doing general search and there's lots of user interaction data and things like that. More the enterprise search model, where you may not have a lot of click data to learn from. And so typically these systems have two components. The first is, a retrieval model or a first stage retrieval model. Here you have a document collection that's been indexed somehow. A question goes in, the retrieval model finds kind of the top K relevant documents, and K can be 100, 1,000, whatever. And then there's some rescoring model, and this is a much heavier, much more precise model that takes these documents and resorts them to create the final ranking that the user will see at the end of the day. And the nature, sort of the computational requirements that each of these stages realizes means that there's going to be different technology that people favor on either. So for instance, in the first stage retrieval, because our document collections are often in the millions or billions of documents or passages or whatever it is you're indexing, things like term-based methods, BM25, TF-IDF, things that we can create inverted indexes from are quite efficient and quite popular. On the neural side, things where we encode questions and passages or documents independently and do a nearest neighbor search are possible as well. On the rescoring side, because we're only going to be rescoring a few documents, much heavier models can be used. And these can be, what people call interaction-based models, cross-attention models. Essentially, we can encode queries and documents or queries and passages jointly because we're only going to be rescoring a few of them. We're not going to be doing it 100 million times or something like that. We're going to focus on neural retrieval. I am going to talk about some hybrid models, but on neural retrieval, there's been a lot of work in the space, both on interaction and relevance-based models. Obviously, recent advances in contextualized pre-training models, BERT, for instance, has led to large gains in this area as well, as true for a lot of text-based processing. And we are going to be kind of working that paradigm here as well. Okay, so first stage retrieval, let me start there. And again, neural first stage retrieval for biomedical literature. First, it's hard to beat BM25. This has kind of been observed for a lot of domains, and I'll show you at least one data set that's also true as well. And part of the problem is we need a lot of data to train these models, like BERT-based model, 24-layer kind of retrieval models. Current data sets that are domain specific to the biomedical domain, we only have on the order of thousands of queries to learn from. And so it's really hard for the models to sort of saturate or really perform well on that amount of data. So there's been a lot of solutions here. One is to use the supervised data and neural models to improve term-based methods. Basically, instead of using unsupervised frequency-based approaches, learn term weights, use click logs or user interaction data when you have it. A very popular one is cross-domain modeling. So if we are building a model for a biomedical domain, instead of training on a small amount of biomedical data, train on MS Marco, natural questions, one of these large-scale general domain data sets, and then maybe fine-tune on a smaller amount of data. What I'm going to focus on here is data augmentation. So actually trying to generate retrieval data that we can learn models specific to the biomedical domain. And I'm going to take a question generation approach. So this has been looked at in the past. Basically, here we're going to make the observation that naturally there's a lot of question-answer pairs available. So this can be data sets like MS Marco and natural questions, these large curated resources, but also things like Stack Exchange, where people just have asked questions and people have answered those questions over time. And even in Stack Exchange, there's a wide variety of topics. They're not huge, but there's even biomedical, chemistry subsets in this data. So the approach here is basically to take all this data. We have millions of examples. We use a 2 million example subset. So we have essentially 2 million answer question pairs or answer passage pairs. And then we're going to train the typical encoder-decoder model, the thing that's used most commonly for machine translation, to essentially take an answer or some piece of text and generate a question from which that answer or that piece of text is an answer to that question, right? And again, we have millions of examples of this general domain on the web. In order to create data specific to the biomedical literature corpus, we then take that model, we take our corpus here, Medline abstracts, PubMed, PMC, full documents, whatever it is. We then, for every document, every passage, whatever the granularity it is you care about in that document, you pass that to the encoder and you get a question that is relevant for that document. And we can do this basically as much as we want and generate millions and millions of examples of domain-targeted data for training these first stage neural models. Right, and that's what we do. So every time we generate a question and from a piece of text, we pass that to the neural model to train the model. So quite simple. To give you an idea of why this might work, here is an example, a real example from our model. This is an abstract, and you can see that the generated question is something like, what is the significance of Friedreich's ataxia? Which this passage here may not answer exactly, but you can kind of see that it's at least somewhat relevant. So it's talking about it and it's talking about the nature of it. So there is kind of a high probability that you're going to find the answer to this question, or at least it has some of the information that you're looking for. And in general, this is kind of indicative of the quality of these generated questions. Even though they're trained out of domain, we can generate a huge number of very sort of fine-tuned biomedical specific questions for training the system. Like I said, we take that data and then we pass it to the neural model just to kind of give some specifics there. It's a BERT-based two-tower dual encoder, whatever you want to call it, model, where we encode the queries and the passages independently. And then we score them at inference time. We use BioBERT as a pre-trained checkpoint. At retrieval time, we encode a query. And then we have our document index, which is just a nearest neighbor search backend. So we have the vectors, we've sort of pre-computed the vectors of the encodings of all the documents in the passage. And then we do brute force nearest neighbor search to get the top K passages. We can distribute that computation and get the top K. And we train this on 83 million synthetic question pairs from PubMed. So to test out, the efficacy of data augmentation for this particular domain, we look at BioAsk year 7 and 8, the document retrieval part of that challenge, as well as the recent Trek COVID data. So we're only looking at round 1, the 30 questions from round 1. And one thing I want to point out is this last row here. Did the annotators the people who annotated relevance judgments, were they also the people that wrote the questions? And for BioAsk, that was largely true, but for Trek COVID, it wasn't true. And we're going to see this actually affects the results a little bit, or we hypothesize that this is the case. So jumping into some results here. So this is BioAsk. I call these zero-shot results because all of the systems reported here don't use any biomedical specific training. We essentially have generated or use other sets of data, so no biomedical literature specific training results, except for we might use the corpus itself in an unsupervised manner. So the first row is BM25, a term-based model. The last row is the model I just described, question generation, QGen. And then the other 3 rows are other neural models, but instead of using synthetically generated questions, we use other techniques to create the retrieval model. The first 2 are essentially masking-based objectives. So we take out a sentence from an abstract, and then we try to predict, was this sentence actually in this abstract, or we do that for an n-gram. So these are other baselines that people have studied in the literature. And this one is cross-domain. So instead of using all those QA pairs from Stack Exchange to create a question generator, we instead just use them to train the neural retrieval model directly. So a couple things here. BM25 is really hard to beat on this data specifically. And this is the one where annotators actually, people who annotated relevance judgments wrote the questions, and it has been observed by others in other domains that when that happens, actually term-based models do end up doing better. But at least in the neural strategies for creating biomedical literature retrieval models, first stage models, the data augmentation, the question generation approach seems to be the most effective. This is the results for Trek COVID. So you can see here that things have actually flipped on their head. So BM25 here is actually worse than the question generation method. And here it's the opposite. The people who did the relevance judgments did not write the questions, right? So it's a more natural data set in that respect. And we can see that there's a big gap here in quality. And I just want to point out that this is not an official submission, which is also sort of why BPref is relatively high in terms of ranking. So inside the brackets here is how our system compared relative to other systems who participated, but other metrics, the rankings are lower. Okay, in terms of synthetic data quality, does actually the quality of generation matter? So we tried larger and larger encoder decoders, so number of parameters, and we can see the pink bars here that our ability to generate questions got better. So that's what this is measuring. The blue bar here is how well we did on retrieval quality. And we can see here that while we were able to do better at generating questions, retrieval didn't really improve. So we think that essentially you pass a bar, a quality bar, where you generate decent questions. And since you can generate millions of them, you actually can do pretty well. And generating better questions doesn't really make a difference. Now, it could be the case that if you were able to generate even better questions, you know, the blue bars would start to pick up. But at least in this experiment, that wasn't the case. Right, so why in some cases does BM25 do better, in other cases neural-based models do better? This can be the memorization versus generalization problem. Neural models fail to capture certain lexical matching things that sort of are more prominent in certain data sets. So here are two examples that we found from our query. It just missed a year, but of course that's important. We actually care about that specific year for that database. This last one here, you know, high triglyceride level versus low triglyceride level. Those terms probably get projected in a similar space. So the model, you know, when it sort of averages encodings or does this sort of aggregation over word level encodings, it didn't really make that distinction, but a user might care about that distinction. So to handle that, we did a very simple hybrid model. Made the observation that TF-IDF-based models like BM25 can be sparse dot products with nearest neighbor search. Neural models are dense dot products with neural neighbor search. So we can just create a sparse dense hybrid where half of our vector, our encoding is sparse and the other half is dense. And K, this parameter K essentially allows us to control the memorization versus generalization trade-off here. And what we can see here, this is the last row for BioAsk, that when we do this, we supersede all the results. So actually now, on average, the model's doing better than both BM25 and the neural model QGen. And this is also true on the TREC data. We can see that having the hybrid model does make a big improvement here. This is actually still just first stage retrieval. So we haven't done anything. We haven't used any biomedical specific resources, labeled data or anything. This is all just data augmentation and hybrid models for biomedical literature search. If we want to add a score, we tried that out as well just to see how things work out. We just used a basic off-the-shelf BERT cross-attention score. We trained it in the same way as Pappas et al. From BioAsk last year, and actually it's almost identical to the model that they use. And so this is comparing our systems to this year's BioAsk 8 results. So the top three systems are the models I talked about before, so BM25, QGen, and the hybrid. These four results are the top reporting systems averaged across all 5 batches. And we can see already the hybrid model, first stage model, is doing you know, basically as well as the top systems in the shared task this year. Once we add this recorder score, so once we add some domain-specific data, then that puts us over the top and we get a nice improvement for either BM25 being rescored or the hybrid model. And this is also true of the TREC COVID results. So adding the rescore helps there, which is not surprising, but it's nice to know that you know, we can still gain, these things are complementary, whether it's data augmentation or using a small amount of data from the target domain does help.
In a couple minutes.
Yeah, great. So I had planned on talking about this more, but I realized I'd be short on time, and now that's been validated. Finding relevant documents isn't the only thing we care about. We also want to extract evidence. So there's a paper that I wrote with my colleagues in Athens. This is the Pappas et al. 2019 paper, where we look at hierarchical models for modeling both snippet or sub-document level relevance and document level relevance in a joint model. And these models, you can see this arrow document and snippet accuracy, extraction accuracy improves when you go from pipeline models to joint models, which is really nice. In particular, snippet accuracy, our ability to drill into a document and pull out the piece of evidence that's useful or supports why we think that document is relevant, increases a lot. And this system was, I think, the best reporting system at that challenge the past few years. So just to summarize, I talked about two things here. The first is synthetic data construction or data augmentation for building first-stage retrievers for biomedical literature, and showed that a question generation approach is an effective approach, and actually on average is better than other methods in the space. When we combine this with term-based models like BM25 into a hybrid model, even very simple hybrid models, there's obviously a lot more complex things we can do even better. So this is basically building from the bottom up first stage neural models for biomedical literature that's quite powerful. And we can make that more powerful if we do start adding some domain specific supervised data. And that's it. So thanks to all my collaborators. Again, thank you.
All right, thanks, Ryan, for the great talk. Let's give people a moment to get their questions into the chat. I guess while that's happening, Lucy does have one question for you. Do you generate questions at different passage granularities? I imagine the types of questions generated at a document level would be quite different from something generated at a sentence level, for example.
Yeah, so right now we basically divide documents into sections, and then we will generate a question at the whole section level. So abstract, intro, whatever. And then we will generate questions at the sentence level as well. Since it's a lot of sentences, we've experimented with things like just randomly selecting sentences or using IDF weights to sort of predict which sentences we think are sort of more contentful. But so far, we found that much of that hasn't really affected the quality of the neural model.
Andrew asks, could you comment further on entity linking and discovery and its impact on QA in scientific literature?
Right, so I'll comment on what we've experimented with. I'm sure there's a much broader answer to that because that's quite a broad question. So what we found actually is that when you ask questions like sort of the question, what regulates the Warburg effect? We sort of use that as our typical question because it has a lot of nice properties. First of all, you have to sort of understand the predicate argument structure to make sure you get the right answer. But actually, more interestingly, there's a lot of things that regulate it. And so what we found is that in order to really show users useful results to that, a very effective solution is to look for answers. So look for parts of the document that answer that question, link that to ontologies, and then cluster by those linkages, doing a hard cluster being the straightest thing. Everything that links to the same node in the ontology, in the knowledge graph, is in the same cluster. And then you sort of show results that way by entities as opposed to just like a list of documents. So on sort of qualitative feedback, we've been told that that's a very useful thing to do, but I don't have any kind of quantitative UX studies on that front. Yeah.